So if we say a function is continuous at some point c, then this is the definition. The limit as x tends to c of f of x equals f of c. If we just say a function is continuous without reference to a particular point, we mean that it's continuous at every point, so that this holds no matter what the value of c is. But it'd be kind of tricky to check that at infinitely many points unless you had some abstract ways of checking all points at once. So here are some quick ways to tell whether or not a function is continuous, or to focus your attention on places where they might be discontinuous. So first, there are several functions that we're familiar with that are continuous. For example, any constant function would be continuous because no matter what the value of the input you're approaching, you get the value of the output of the function, because the limit of a constant is the constant and the output of this function at any point is the constant. Similar idea with the basic identity function x. The limit as x tends to c of x is c, which would be the value of the function at c. So that's got to be a continuous function that it matches up no matter what value of c we choose. Also, e to the x is a continuous function. ln of x is continuous, although for ln you can only plug in numbers that are greater than 0, so it's continuous as long as x is greater than 0. You can assume that sine x and cosine x are also continuous. So these are all sort of basic building blocks of functions that we know are continuous. Once we have those basic building blocks, we can build them to make more complicated functions, and there are some ways of building functions that we know will lead to continuity. For example, if we have two functions that are continuous at a particular point, then if you add those two functions, you get something that's continuous. So, for example, if I had this function, if f of x was x and g of x was sine x, those functions are continuous everywhere. So I know that if I add those up to make a new function, x plus sine x, since that is the sum of those two continuous functions, it is also continuous everywhere. Same thing if I were to subtract them. If I had done like x minus sine x, or x plus e to the x, that would be continuous. A product, so for example, if you made a function that was x times e to the x, this is a continuous function, that's a continuous function, so the product of two continuous functions will be continuous. Constant multiple, if you take a constant times a function, you know that that's going to be continuous. That's really just a product of two continuous functions. So, for example, if we made this function h of x by taking 2 times x, that's a continuous function. X is a continuous function. The product of two continuous functions is continuous function. Quotients are continuous, except where the denominator might be 0. So that's one that we can watch out. So watch out for places where the denominator is 0 on a quotient of functions. Denominator is 0. If you take some function to a power, then that's going to be continuous. Same if you take a root, just has to be something that's so that it's defined in an open interval containing c. Okay, so if we take, like, if n was a positive integer like 2, like the square root, that would be continuous. It's even, I guess, continuous from the right anyway at 0. Okay. So another thing, if you have a composition of continuous functions, that will be continuous as well. So for example, here's a continuous function, x squared, right? You could think of it as the product of x with x, so that's got to be continuous. And here's a continuous function, e to the x. So if we find the composition of those two functions, what we mean is to take x, plug it into f, and then plug it into g, which would be g of x squared, and g takes whatever you give it and makes it the exponent on e. So this is a composition of two continuous functions. It must be continuous. So e to the x squared is continuous. Alright, so compositions of continuous functions are continuous. So let's look at some examples, and we'll just try to use these laws quickly to figure out where these functions are continuous. Well, this function is going to be continuous everywhere, right? Because we can always take, for any number, we could always take the fifth root because it's an odd kind of root, so this function is continuous everywhere. You can see what we're saying basically is that the fifth root function is continuous, and 2 minus x is continuous, and so their composition is continuous. So you think this is our outside function, and our inside function is 2 minus x, then this function is really just g of f of x. The g just takes the fifth root of whatever you give it. So since the inside function is continuous and the outside function is continuous, that has to be continuous. So this is continuous everywhere. Alright, now this function, let's see, that's definitely continuous, right? 1 is definitely continuous. This is a ratio or a quotient of two continuous functions, and this is definitely continuous because it's x plus 2, which is a continuous function, raised to a power. The squaring function is a continuous function. So, but when you make a quotient of functions, you have to watch out for where the denominator is 0. In this case, we would have trouble if x plus 2 was equal to 0. That would mean if x was negative 2. Our function's not defined at negative 2, so this is continuous except at x equal negative 2. This. Well, let's see. Absolute value is actually a piecewise function, right? If the number is positive, you just get back the original number, but if the number is negative, the absolute value gives you back the opposite of that negative number. So this is continuous, and that's continuous. So we're definitely continuous if x is greater than 0, and continuous if x is less than 0. The only question might be what happens at 0. Is it continuous at 0? Let's see. I guess. Yeah, so the value of the function at 0 is 0, and you can see that the limit as x tends to 0 of the absolute value of x is also 0, because if you take the absolute value of numbers that get closer and closer to 0, the output gets closer and closer to 0. So yes, it's continuous at 0, so this is continuous everywhere. Everywhere. There we go. Okay, what about this one? This is built out of some things. Well, x is continuous, so x squared is x times x. That's the product of two continuous functions. That has to be continuous. This is times a constant 1/2, so that has to be continuous. And then this function, the top is continuous, and the bottom, 1 is a continuous function, absolute value of x, we just saw is a continuous function, so that's continuous. And this denominator is never 0, because this is always at least 0. At least 0 plus 1 is at least 1, so this denominator is never 0. So this has got to be a continuous function because it's a quotient of two continuous functions and the denominator is never 0. We have one continuous function minus another continuous function. This has to be continuous everywhere.